Okay, we're going to talk about some operations with square matrices. In particular, we're going to look at the inverse of a matrix and how we could use that. Okay, so we'll check to see if two matrices are inverses of one another and what that means. We will look to find the inverse of a square matrix, and we will use inverse matrices to actually solve problems. Okay, so first of all, a square matrix is simply a matrix that has the same number of rows and columns. So a 2 by 2, a 3 by 3, a 10 by 10. Same number of rows and columns would be referred to as a square matrix. Okay, and the identity matrix is a matrix that we can multiply a square matrix by and get the same matrix that we started with. Just like multiplying by 1 gives us an identity in the real number system. Okay, so 1 times 5 is 5, for example. The same thing with an identity matrix. An identity matrix times some matrix equals that matrix. Okay? Identity matrices all look the same, depending on their size, of course. They have 1s down the diagonal, just like these do, and they have 0s everywhere else. Okay. Okay, so to test to see whether two matrices are inverses of one another, what we do is we multiply them. And what we're hoping is that this is going to come out, and we'll kind of make it a question mark, is this an identity matrix with 1s on the diagonal? Now, if we're testing to see whether A and B are inverses of one another, we need to check the multiplication in both directions. Both of these have to come out to be an identity matrix. The symbol for an inverse of a matrix is similar to the symbol we use for the inverse of a number. A to the negative 1 is the inverse of matrix A. Okay? That does not mean 1 over matrix A. It means the inverse of matrix A. Okay. Now let's do a quick test. I have these in the calculator already, so I'm going to bring up the calculator, and hopefully it works on. And just to check, I'm going to go to second matrix, and let's look at matrix A, and that has that correct matrix in there. I have matrix B in as well. So what I'm going to do is then do let's clear this, second matrix A times second matrix B, and what we're hoping is that this comes out to be an identity matrix, and it does. Okay, that in and of itself does not prove that these two matrices are inverses of one another. Okay, we have to check in the other direction, so we have to multiply B by A. So let's do that. Second matrix B times second matrix A. And that is an identity matrix as well. So now we could say that A and B are inverses of one another. Now you may want to do some testing, or you may already know that the multiplication of matrices is not commutative. So A times B does not necessarily equal B times A. That's why you have to test both. So again, if we have square matrices, the multiplicative inverse of a matrix is denoted with this symbol, and A times its inverse is the same as the inverse times A, and that will give you the identity matrix, that matrix with 1s down the diagonal and 0s everywhere else. Okay. So we want to show that B is the inverse of A. Okay, and what we need to do is go ahead and multiply these out. Now we could do this on the calculator, or we can do it manually. I'm going to do it manually real quickly. I need to multiply A times B, and I also need to multiply B times A. All right, well, let's do A times B. It's going to be a 2 by 2 matrix. Okay, it's going to be across and down. Remember that. So negative 1 times 1 is negative 1, plus 2 times 1 is positive 1. Okay, let's go for this element here. It's going to be negative 1 times negative 2 is 2, plus 2 times negative 1 is negative 2, so 2 plus negative 2 is the big old 0. Okay, going for this bottom left element, -1 times 1 is -1, plus 1 times 1 is 0. And for this element is going to be -1 times -2 is 2, plus 1 times -1, or 2 plus -1 is 1. So that gave us the identity matrix. So far so good. In order to actually finish confirming this, we would have to multiply b times a. I'm not going to do it here, but you can go ahead. And this should also give us an identity matrix. If it does, then these are inverses. If it does not, then they're not inverses. Okay, so a couple things. A matrix that has an inverse is called invertible. So if we can take an inverse of a matrix, we say that matrix is invertible. You could only invert a square matrix. Okay, so if it's any other dimensions where the dimensions, the rows are not equal to the number of columns, you cannot have an inverse. Okay, not every square matrix has an inverse, but if it does, that inverse is unique. Okay, so we're going to go ahead and try to find the inverse of this matrix. And we know that if, let's let X be our inverse matrix, we know that A times X is going to be the identity matrix. So we could write this as A, 1, -1, 4, -3, times X. And I'm going to write it all out. This is X sub 1, 1, X sub 2, 1, X sub 2, this is not 2, this is 1. All right, X, row 1, column 1, X, row 1, column 2, X, row 2, column 1, and X, row 2, column 2. And that would have to equal an identity matrix, which is just going to be this. Now we could write out our multiplications. If we were to multiply this across and down, all right, so let's build a matrix. 1 times x11 is x sub 1, 1, plus 4 times x21, plus 4x sub 2, 1. Okay, and this is still going to equal 1, 0, 0, 1. Okay, let's go for this one. This is going to be across and down. It's going to be x1, 2 plus 4 x2, 2. Down here, we're going to go across and down, -1 times x1, 1 plus -3 times x2, 1. And our last one is going to be -1 times x1, 2 minus 3x2, 2. Okay, and that equals that. Now, if I'm not going to go through all of this, but we could set up some systems of equations here. I know that each of these elements, in other words, this element, has to equal its corresponding element over here. Okay, so I could say that x sub 1, 1, which is just a variable, plus 4 times x sub 2, 1 equals 1. And then I can continue on. I could create another expression with this one. Let's do across. Okay, I'm going to go for this element being equal to this one. Okay, so it's going to be negative x sub 1, 1 minus 3x sub 2, 1 equals 0. And you can see I could do the same thing for this element is equal to 0, and finally the last element as well. That would be this element would be equal to 1. Okay. Now, I can go ahead and solve this. Okay. If I add these up just using elimination, this is going to cancel. 4 minus 3, or 4 plus -3 is just x sub 2, 1, just one of them, equals, and we're adding, so this is going to be 1. So I know that x sub 2, 1 equals 1. I could then go back and substitute that in here and find out what x sub 1, 1 is, and then continue on in the same way, create 2 more equations for the other 2 elements, solve them all out. If you want to go ahead and do this, you should get a solution of -3, -4, 1, and 1. Okay. Now you could verify that inverse by multiplying, and you should get the identity matrix in both directions. So A times this inverse, this would be x, by the way. So you would multiply A times x, and you would multiply x times A. In both cases, you should get that identity matrix. Okay, I'm not going to do that. You could imagine that this would get a bit messier doing it with 3 by 3 matrices. Okay. One way that we have to help us figure out the inverse of a matrix is using what's called the determinant. And the determinant of a 2 by 2 matrix is nice and easy. All we do is we multiply the diagonals and subtract them. So we take this diagonal, which is A times D, and we subtract off the other diagonal, which is C times B or B times C. Okay? And we come up with a number. That number we refer to as the determinant of the matrix. Now, there are 2 symbols or 2 ways of writing the determinant of a matrix. One of them is DET, determinant of matrix A. The other one is this, which I don't like, and the reason I don't like it is because it can easily get confused with just a matrix, right? Because it's only differing by the little lines here. Or it also looks like something else that we've dealt with, which is absolute value, which it's not either. So I prefer not to use that, though it is not incorrect, and you may see it. Okay. I am going to pause here, and we will take up this lesson in the next video.